afterwards for whomever wants to watch it.
Yep, that's fine.
And I think now you're probably on YouTube. So speaking
I'll start being careful as to what I say.
Yeah, so let's not say anything about politics, anything about, you know.
You're no fun.
Is that a caipirinha?
That's for you to guess. I wanted to feel like I was visiting you guys properly.
Because you said you were going after some lime. Did you?
Well, you can see.
Okay.
Paulo.
Yeah.
Should we start to record?
Yeah, I think we should start to record, and I think, given it's 4:06, we can start.
Hi, Manfredo.
So I'm
okay.
Recording here.
Recording here too. Okay, Paulo, could you introduce our next colloquium speaker?
Yes. So I was wondering whether I should speak in Portuguese, open this up in Portuguese, or in English. I'm already speaking in English, so please, I'd like to, welcome everybody to the physics colloquium. We are now back and having a series of colloquia every week on Thursdays at 4 p.m. São Paulo time. But one of the good things, if there is any solace we can take in this pandemic, is the fact that now our speakers can come from anywhere in the world. We don't have to rely on them traveling all the way over to Brazil to give a talk. And so it's an enormous pleasure to have Aephraim Steinberg from the University of Toronto give the talk today. I would, of course, much rather have him physically present here, so we could share caipirinha as he himself. And I think the last time we saw each other was at the conference that we organized in Marizias, and so that was really a caipirinha fest, and deeply missed. I should say I've known Aephraim for quite a long time now. I don't remember exactly the first time we met in person, but we've met a lot of times at conferences and other places. He's been on the faculty at the University of Toronto almost the same time I've been on the faculty at the University of São Paulo, but he's younger than me. Which means, I'm 32, so you must be what, 30?
I'm going on 16.
Aephraim was a PhD student in Berkeley under the guidance of Ray Chow. He managed during his PhD to spend some time in Paris at the École Normale Supérieure, which is a place where I did my PhD. I think we actually overlapped there sometime, but I don't remember meeting you at that time. He was hired at the University of Toronto very soon after his PhD. I'm not going to talk about all the awards and nice recognition he's had. Aephraim is somebody who's been working on correlations, entanglement between individually generated photons. He's been interested in this problem of measuring how long a particle can stay in a place where it should never have been in the first place. And I know that generations of students have worked on this. I've followed this, with interest, not extremely closely, but I followed the story since he was planning on doing these experiments. And we've had the nice interaction of having two former students of our lab go do postdocs in Aephraim's lab. One of them is Professor Marcelo Martinelli, who's now full professor in our institute. And very recently, Aephraim had results from this long-going experimental saga So it felt like the perfect opportunity to ask him to give a talk to the Physics Institute. So thanks, Aephraim, and we are very, very anxious to hear you.
Anxious. Well, thank you. It was an extremely kind introduction. It was a kind invitation. I'm happy to be your solace of quantum in these odd times. Like you, I'm sorry that it couldn't be in person. I always love an opportunity to visit you in person, visit Brazil, visit your labs, etc. Let me first say the title here is a little bit strange. What I want to tell you about is measuring the tunneling time and other problems in quantum archaeology. So as Paulo said in the introduction, I've been thinking about tunneling times for many years, but in fact, thinking about that problem as a grad student got me interested in a broader problem, and that's the perspective that I want to be taking now. I'll explain a little more what I mean by that, but I want to begin first by acknowledging all the people who really did the work I'm going to be telling you about now. The work on tunneling times on our Bose-Einstein condensate is on an apparatus that was originally pioneered by Anna Joffrey and Mirko Zirke, but the recent work, the recent publication, was led by Ramon Ramos, along with David Spearings and Isabel Racicot. Now that work's been continued by David, helped by Joseph, Nick, and Grace, as you see over here. And I'll also tell you at least a little bit about some of our more recent work, not yet published, that's being led by Josiah Sinclair, along with Daniela Angulo Mercio and Kyle Thompson. All of this work has benefited from the theory collaboration of my postdoc, Aaron Brodich, and of course, some kind funders listed on the bottom. And here's the perspective. What do I mean by quantum archaeology? We all know, thinking back to the Bohr-Einstein debates, that one can't look at present observations like where on a screen a particle lands and draw conclusions about what it did to get there. We can't ask which path it took on its way. On the other hand, classically, we do this all the time, and it's a cornerstone not only of our day-to-day thought, but also of many fields of science. And archaeology is one example. Cosmology is another example. You look at a bone or you look at the cosmic microwave background and you draw conclusions about what was there 65 million years earlier or 15 billion years earlier. Now, I think this conventional wisdom dividing the quantum world and the classical world is very misleading. And I would remember that as far as we know, there is no classical world. So when you look at that bone, you're looking at a quantum dinosaur bone. And when you conclude that the dinosaur used to walk in Missouri or wherever it was, you're making a conclusion about the past of a quantum system. So we do know from our everyday lives that you can draw conclusions about the past of a quantum system, even if you can't know exactly what the trajectory of a photon in a two-slit interferometer is. So the question that excites me is, in general, how much can we say about the history of quantum systems? When I make an observation now, how much do I learn about the past? And there's a very simple kind of straw man example of this that I always use to illustrate it. Some of you may have heard this before, either from me or elsewhere. But I think that you're familiar, as I was growing up in New York, with the way that people on the street like to try to cheat tourists out of their money and hide a $1 bill, or with inflation, it's probably a 20 by now, under one of 3 shells or one of 3 boxes, and mix them up and ask the hapless tourist to figure out where it's sitting now. And what I want to suggest to you is to consider a quantum version of this. Suppose I took a bill, and instead of putting it in one box or another, I put it in a superposition, a plus b over root 2, and asked you to figure out where that bill was sitting. Now, we all know you can't tell me with certainty. It could be an A, it could be an B, and I'm not going to cheat you that blatantly. I'm going to give you extra information. I'm going to promise you that when I later look for this bill, I find it. But I find it in a different superposition. I find it in b plus c over root 2. And my question to you is, given these 2 pieces of information, do you know more than you did just from the A plus B? Can you make predictions, for instance, about things like what is the probability that the particle was in B between my preparation and my finding the particle? I'm not going to try to do this interactively on Zoom. I've often done this interactively in meetings. And I'll tell you the basic result, which is the following. Physicists who haven't already thought about this specific problem are generally pretty silent, or say you're not allowed to ask that question, or just very simply say, well, I prepared it in A plus B over root 2, and therefore there's a 50% chance that it's in B, and making a measurement later may disturb it after the fact, but it can't fundamentally change that. Non-physicists, when I give this as a public lecture, there's always someone in the audience who immediately guesses what I think is the right answer. And the right answer is that it's in B with 100% certainty. And you can see this if you think classically, if you forget your quantum mechanics, and you just think, well, he told me he was going to put it in either A or B, and he told me he found it in either B or C. It obviously couldn't be A, or he would never have found it in B or C. And it also can't be C, because he put it in either A or B. So by process of elimination, it must be in B. And the interesting thing to me is physicists don't know whether or not it's fair to turn that plus sign into the word or, whether that reasoning actually works. And there is an experimentally well-defined sense in which it really does. And the answer is that it acts as though it were 100% in B. And I think this shows a gap in our intuition. I mean, we can do the full calculation. I can show you the answer, but we shouldn't need to work that hard, right? Our intuition should be good enough that we can do as well as the man in the street and say it was B. So this is just my big picture for why do we need to work harder to understand post-selected quantum systems. So here's the outline of my talk. I'm going to go into the particular problem I'm interested in, tunneling times, and that's got a century-old history, so I'll say a little bit about it. And then I'll tell you about our recent result, our experiment that probes how much time a particle spends in the allegedly forbidden region before being transmitted. And that's the post-selection. I'm interested in what happens if I see the particle got to the far side of the barrier. Do I learn something extra from that fact? Then I'll try to tell you with varying degrees of acceleration about some ongoing and future work. In particular, what it would mean to ask where inside the barrier the particle spends its time. Also asking whether observation itself perturbs tunneling by looking for the particle in the barrier. Do I collapse it? What does that do? And then I'll at least advertise this completely different experiment. When a photon traverses an atom cloud instead of atoms traversing a barrier, how much time does it spend inside the atoms? And I think we've learned some really interesting things there, and there are more open questions. All right, so let us begin with the background of tunneling. You're all familiar with tunneling. There's an illustration. We're imagining a particle that has energy less than the height of the barrier. And of course, there's an exponential decay of the wave function inside the barrier, but then some probability to find it on the right-hand side. We all learn how to calculate this in our first quantum mechanics courses. But interestingly, most people have never heard the question and likely never asked themselves the question, how long does it take to get to the other side? Now, that's such an obvious question that you shouldn't imagine that no one asked that back in 1926 or 1932. They did. And if it's not taught in the textbooks, it's not because no one calculated the answer. I really think it's because the answer was so confusing that we were scared to bring it up in front of our students. We didn't want to raise something that we didn't really know how to explain. You could think about the problem semi-classically, right? Just to ask, what's the velocity of a particle as it propagates? And for that, I need to look at the kinetic energy. So I take the energy minus the potential. I'm left with the kinetic energy. I take the square root. It gives me a velocity. D over V is a time. And as I lower the energy towards the barrier, that kinetic energy goes to 0 and the time diverges. Of course, as you go further than that, you end up with E less than V naught. You have negative kinetic energy. And if you attempt that semi-classical approach, you get a negative kinetic energy and imaginary velocity. And we, of course, don't know what an imaginary time would be. But we're not stuck with that. There's a very simple way that I think we've all learned for dealing with wave propagation. On the upper right here, you see a video that I stole from Wikipedia or something. We know how to do these time-dependent solutions. And you could just ask, if I know at which time the peak is moving towards the barrier, can I calculate where the peak of the transmitted particle is and ask how long it took to get there relative to what it would have done under free propagation? And the way we know how to do that is the stationary phase approach. That's an approximation, but it turns out it's a good approximation here. It gives you what we're used to as the group velocity. But here's the problem. Remember what the wave functions look like. Up here in the barrier, We have a e to the minus kappa x plus b e to the plus kappa x. The stationary phase method asks how much phase has been accumulated by the time you get to the far side, and then takes a derivative of that with respect to the incident frequency. The thing is, the real exponential decay doesn't contribute any extra phase. So the phase over here on the right side becomes essentially independent of the thickness of the barrier. And that means so do its derivatives. So what you find is a time that becomes essentially independent of the thickness of the barrier, at least for thick enough barriers. And this is part of what confused people back in the 1930s, 1950s, 1960s. If the time delay is independent of d, the thickness, then for large enough, wide enough barriers, it can be less than d over c, and that can seem to violate relativity. The particle can seem to arrive sooner than it would have if it had been traveling faster than the speed of light. You might say, all right, Schrodinger equation is non-relativistic. I don't worry too much about these things. That's not the right resolution. People redid this problem using relativistic equations like the Dirac or Maxwell equations. The same thing occurs. Moreover, people did experiments, including me with Paul Kwiat and Ray Chow in my PhD thesis, a number of other groups as well, confirming that this really is what happens for the peak of the wave packet. Nicole, who first wrote this down, and Hartman, who famously pointed out that saturation as a function of distance, were correct. And the peak can travel faster than the speed of light. Here's just some data from my thesis. I got really worried that people would just claim we had made a sign error somewhere, so we made sure to change the parameters so you could go from this left-hand region where the time is negative with respect to the vacuum propagation time to a region where it's positive. So at least if I made a sign error, one side or the other was going to be faster than light. We could conclusively show that we had seen that. Now I'm going to go through two asides. You should clearly be worrying. Does this mean energy is propagating faster than the speed of light? No, it does not. This occurs for thick barriers where the tunneling probability is very small. And I've illustrated that with some Gaussian tortoises or snails or something like that, attempting to tunnel through a barrier. And what you notice is that the particle that had to tunnel, wave packet 2 here, has a peak that crosses the finish line before that of wave packet 1, which was just propagating at c. But the height of this Gaussian is so much smaller that at every point in time, there is less probability to detect a particle if you put the barrier in the way than if you don't, or there's less energy reaching the finish line at any point in time with the barrier than without the barrier. So you don't need to postulate faster than light energy transmission. You just have to accept that for some reason, the energy that's being transmitted seems to come preferentially from the front of the wave packet rather than uniformly across the wave packet. So this was understood for a long time. When we were working on this, I was more concerned about the information problem. When the photon appears, have I captured information faster than light? But the answer again is no. We worked this out using Gaussian pulses that go on forever, which means that there's no point in time where you actually learn anything new from the signal. What I mean by that is if I give you some portion of a Gaussian, you can Taylor expand it and predict its future perfectly. That's true for any analytic pulse. We can even go deeper and think about how this arises in some tunneling geometries. Some of them amount to interference. I think this is the clearest picture for that. It turns out that when light, for instance, gets transmitted through a 99% reflective mirror, you're getting destructive interference in the forward direction. There are many, many different paths with multiple reflections, but each one is out of phase with the path before it. And when you add up all these wave packets, each one a little more delayed, the result is a Gaussian wave packet that looks just like the incident one, but is shifted forward in time. And that's a perfectly causal Green's function. It's simply a sum with alternating phases of different Gaussians with positive delays. And in this sense, the tunnel barrier, the mirror, is acting like a kind of analog computer. It's taking these different moments in time and predicting if we have a low enough bandwidth pulse, if the pulse is analytic, what do we expect the future to look like? And as long as the pulse varies smoothly enough, that Taylor expansion works. And it looks as though you've advanced the pulse in time. If, however, you had a large bandwidth, a non-analytic pulse, this would all break down. And that's illustrated with this delta function at the bottom. If instead you sent in a delta function, the fastest thing that would get out would be the one that propagated with no reflections at the speed of light. And all these other reflections would just be delayed relative to that. And nothing would travel faster than light. I don't want to harp on this too long, but it's hard to bring up faster than light tunneling without having people worry about these two questions. So we need to begin with that. And this, I think, still had a lot of people confused in the 90s, but some experts had really already resolved these two problems in their minds. In particular, Büdeker and Landauer, who were very concerned about applying questions about tunneling time to condensed matter systems, had come to the conclusion that even if the group delay was right, it simply wasn't telling us anything physical, that there was no causal connection between the incident peak and the output peak. And one should then instead find other ways of defining the amount of time a particle spends inside the barrier. This was an article of Landauer's about 30 years ago, making the distinction between how long a particle bounces around, let's say inside a trap or a nucleus, before it escapes, and how long it spends inside this barrier, depicted here by this narrow tube, while it's finally escaping. And Rolf wrote that the time taken by that final event had now, in 1989, been measured in a subtle and definitive experiment by a group at Saclay. These are the results from Daniel Estève's group at the time, and it's a little bit indirect. I don't want to go into details, but basically they were looking at macroscopic quantum tunneling of a squid, and then they added a delay line and a short that led to an extra reflection that could interfere with the dynamics inside the squid. And their idea, based on Büdeker and Landauer's reasoning, was if that reflection occurs before a tunneling event is complete, it can change something about the dynamics of the tunneling. Whereas if I have a really long delay line so that by the time the reflection gets back, the tunneling event is already over, that should no longer have any effect. So this plot here is a time versus a time. It's the characteristic decay time versus the length of that delay line. And based on the critical behavior of this curve, they extract an order of magnitude for the duration of the tunneling event, which you see in their case was about 78 picoseconds. So that was 30 years ago. Sorry, I couldn't help showing a picture of this. A few years ago, I had the luck to meet Daniel Estève for the first time. And when I told him how impressed I'd been by this experiment and how many years I'd been thinking about it, he said, oh, well, just hold on a second. And he reached up into his bookshelf and handed me this device, which was the device from the first tunneling time experiment. And it's fascinating to me to look at it because this is the grandfather of today's superconducting qubits. You look at this paper, you see Daniel Estève, you see John Martinez, you see Michel Devoré. This is exactly what evolved into the qubits you see today. And although it seemed like this remarkably sophisticated mesoscopic physics to me at the time, by modern standards, this looks like such a simple handheld device. I think that's really cool. Is it, however, the end of the story? I can't see any better way to answer that than by trusting the popular press, who about 2 years ago were again writing articles saying that physicists had solved the great mystery of the quantum world, and in particular said that quantum tunneling is so fast it could be instantaneous. And I already said that yes, it can be fast. This instantaneous gave me some pause. This is a fascinating Nature paper, by the way, to look at. Even if I disagree with some of the claims in the popular press, the experiment is beautiful. Well, this is good motivation to keep working on the problem. And what I want you to take as the perspective is that we need to define the time by thinking about what it means to have a clock. And this is kind of a relativistic idea. This is how Einstein thought about time and space. And this is basically what Büdeker and Landauer were doing. They were saying, what do we mean when we ask how long was a particle interacting with some tunnel barrier? And the picture that we had, redrawn much better by the artist of Scientific American and what I've reproduced here, is if only these particles could hold on to their own stopwatches and press the start button only while they were in the barrier, and then press the stop button when they got out, we could read off how much time they were in the barrier. And that's very different from just asking what's the most likely time to see a particle get out if it gets out. It's a completely different quantity. So one way you could imagine defining that goes back to Bose and Rybachenko in the 1960s, but was really honed and popularized by Büdeker in 1982 or 3, I forget, 2, I think. And it's called the Larmor Time. It is very simple. Let the stopwatch, the hand of the clock, be the spin of a particle. So imagine an electron that's spin polarized along the x direction over here, approaching a barrier. But inside the barrier, confine a magnetic field along the z direction, so that while we're in the barrier, we know that we'll precess at the Larmor frequency. Now, if the particle is transmitted, you can look at the angle of the spin, that precession angle, and divide by the Larmor frequency, and conclude how long it was precessing for. There's the stopwatch that was only ticking while you were inside the barrier. So this was the idea of our experiment. By using this Larmor clock, this stopwatch, we're going to try to weakly measure the time an atom spends in the barrier. I'll come back to the word weakly later on. So what is the actual experiment? I've been talking generalities until now. Now let's get into the nuts and bolts, or the atoms and the lasers. The atoms are rubidium-87. To get a long enough coherence length that we can see significant tunneling, we Bose-condense them. We cool them further until they have a coherence length of about 4 microns. And that's important because that's larger than the wavelength of light. So I can take a 420 nanometer laser beam that's a little bit blue-detuned, making a repulsive barrier for the atoms, and focus it down to about a micron. And the width of the barrier is now shorter than the thermal de Broglie wavelength, or the coherence length of the condensate. So I can expect to see some significant tunneling. We Bose-condense the atoms inside a crossed dipole trap. And we're going to use this horizontal beam as a kind of waveguide to let the atoms keep moving in one dimension after we remove the other beam. So they'll cross this blue barrier while moving in one dimension. That blue barrier is adjusted to have a barrier height of about 150 nanokelvin, which may sound very small, but we've lowered the temperature of the atoms to 1 nanokelvin. And that 150 nanokelvin corresponds to an incident velocity of about 4 millimeters per second. So what that means is, oops, there's a little digression here about the cooling. I don't think the digression is that important, but I can't resist showing you the video of the first time we were able to put atoms on top of one of these barriers. Here we've made a horizontal sheet of light, and we've just sat the BEC on top of it. And what you see is that some atoms have such high energy that they just fall right through the barrier, but the others just spread out smoothly along that table and fall over the edges. What you don't see is that all this time, there's some atoms still leaking through, too few for us to see. And in the recent experiment, those, of course, are the ones that we're trying to probe. But sorry, what I wanted to say, I seem to have lost track of the video, is that if we now push these atoms with a magnetic field towards the barrier at about 4 millimeters a second, half of them will be transmitted and half of them will be reflected. At 5 millimeters per second, they're almost all transmitted. At 3 millimeters per second, they're almost all reflected. So that's going to be our tunneling experiment. Now, we also need this probe. We need this fictitious magnetic field. I say fictitious because I don't really know how to confine a real magnetic field to a 1 micron region. What we do know how to do is use laser beams to couple 2 different states of an atom through a Raman transition. And those 2 different states, of course, act like a spin 1/2, and the coupling acts like a magnetic field. So we can use either an additional set of laser beams superposed on the barrier to act as this effective magnetic field, or in our case, because it was difficult enough to focus one beam down, let alone focus something else more tightly, just use the barrier itself by modulating it at 6.8 gigahertz as an additional Raman beam. That way, only while the atoms are inside the barrier do they see this pair of beams, and they get driven between 2 hyperfine states of the atom, the F equals 1, M equals 0, and the F equals 2, M equals 0, which we use for the same reason that these are used in atomic clocks, which is that they're highly insensitive to background magnetic fields and noise, and that's what allows us to do these very small rotations and measure precisely the rotation angle. Finally, here's the video I was looking for earlier. We've condensed the atoms in this cross trap. we add the barrier and we turn off that transverse trapping beam, so that now with a little bit of a push towards the barrier and the Raman beams they compose, some atoms are transmitted and some are reflected. And we can now imagine measuring the spin of the transmitted atoms, dividing by the Raman-Rabi frequency, the effective Larmor frequency, and telling how long they are interacting with those beams. So first we calibrated on a free wave packet. This picture on the left is what happens after the atoms that begin in the plus X state go through a region where we've initially turned off the barrier. So everything is transmitted to the right, but we do a Stern-Gerlach separation of the plus X and minus X after this interaction. And we see that there's some population in X, some in minus X. We can do the trigonometry and figure out what the angle is. And in the end, this was a 20-year, $1 million, I don't know how many man-hours experiment to conclude that the time an atom spends in a region goes as 1 over the velocity that it has while traversing that region. We're very chuffed to see that that indeed worked. But more to the point, this allowed us to calibrate the Rabi frequency, the Larmor frequency that we have in this experiment. And now we can turn the barrier back on. Here's a picture taken when the barrier height is very close to the kinetic energy of the atoms. So about half are transmitted and half are reflected. And if you look closely, you can see that the ratio of these plus and minus X spots seems to have changed. So here's early data, and I want you to take it with some salt because things have changed since then. But what's suggestive is that you see that as we lower the velocity, this time grows, but instead of diverging when the velocity or the energy just comes down to the barrier height, indicated by this vertical dashed black line, it's in fact finite at that point, as everything should be quantum mechanically, right? It cleans up all of our divergences. And then it begins to come back down. And that's one of the really striking predictions, both about this interaction time and in fact about the group delay as well, that lower energy particles can tunnel faster than higher energy particles. They're less likely to get across, but if they do get across, they're quite fast. Now, why do I say to take it with a grain of salt? In part because of our error bars and some systematics we were still cleaning up, but in part because of exactly what Buedeker figured out almost 40 years ago now, which is that measurements disturb the system. Now, we all knew that. Bose and Rybachenko had hoped that by taking the limit where this magnetic field was really small, they could neglect any additional disturbance. And that as long as the precession angle divided by the Larmor frequency tended to a constant in the limit of very small magnetic field, that would be a good measure of the time. Buedeker looked back at it, and here's how you analyze the problem. Obviously, this spin X electron is just a superposition of up and down. Each one of those is here an energy eigenstate, because one is aligned with the magnetic field and one is anti-aligned with the magnetic field. But the one aligned with the magnetic field sees a slightly lower potential because of that dipole-dipole interaction. And therefore, it's more likely to tunnel to the right-hand side. The one that's anti-aligned sees a higher potential energy, and it's less likely to tunnel. So in fact, if you look at what's transmitted, you see preferential transmission of the spin up. You also see a relative phase between the two, and that's what gives rise to the precession that Bose and Rybachenko expected. But you see a full three-dimensional rotation, some tendency to precess, and also some tendency to align with the magnetic field. Notice that this only happens because we're post-selecting on the transmitted atoms, right? S sub z commuted with this Hamiltonian. So if we looked at all the atoms, we'd still have 50% up, 50% down. It's just that more of the downs got reflected and more of the ups got transmitted. So the post-selection is what creates this possibility of an out-of-plane alignment angle. Excuse me. So Buedeker, pointing this out, found furthermore that both of these effects are first order in the magnetic field. So you can't simply take the limit of small b and get rid of one of them. And in fact, in the regimes he was interested in, the alignment effect was much bigger than the precession. So he said, look, there seem to be two components, theta and phi, or theta z and theta y, he called them. What should I do? And he just decided to add them in quadrature and look at the full three-dimensional rotation angle. I don't think there's any great justification for doing that. I think he liked it because it gave him a result he had other reasons to believe. And he said, well, let's be optimistic and take that as the right answer. The interesting thing is that there were other approaches that also gave two different times. In particular, one due to Sokolovsky and Baskin, which involved Feynman path integrals and gave a complex number, as Feynman path integrals always do. The interesting thing is the real and imaginary parts of that complex number correspond precisely to the two angles we see here. Except at the time, no one knew what to do with complex times or real and imaginary parts. And I would argue that now we do understand what to do. Based on the weak measurement formalism of Aharonov, Albert, and Weidmann, which was published a few years after this Larmor clock work, we understand that the real part of what I call a weak value, in this case, the precession angle in the XY plane, corresponds to the effect of the system on the pointer, the expected change in a pointer position, a classical measurement result, in other words. While the imaginary part, which here corresponds to the tendency to align with that magnetic field, is something purely quantum that really has to do with the back action of the measurement. It doesn't tell you so much about the sensitivity of the pointer to what the system is doing. It tells you rather about how sensitive the system and its post-selection are to the interaction with the pointer. So to separate all these things, it's not enough just to measure one angle. We needed to do full tomography on the spin. And Ramon and David figured out how to do that. And here are pictures along the Bloch sphere at very high velocities. We began along the x direction. We spend very little time in the barrier, so the spin ends up almost along the x direction. But as you lower the velocity, the particle spends more and more time interacting. You see more and more precession angle, but also more and more alignment. Here in the xz plane, you see that the lower the energy of the particle, the more you tend to align with z, but also the more you tend at first to precess towards y. So we can summarize all those data. I'll apologize in advance for a very busy plot. Versus velocity of the incident particle, where about 5 millimeters per second here is the barrier height, we can plot both the in-plane, or real time, and this out-of-plane, back action time. And I've compared them to a few theories, but there's an experimental complication, which is that our wave packets still have some width in velocity. And the transmission is much larger, of course, at higher velocities. So if we send in a wave packet centered at 4 millimeters per second, what actually gets transmitted is not the stuff at 4 millimeters per second. It's the stuff off in the Gaussian tail around 4.5 millimeters per second, but that had a much higher transmission probability. So that's why from these ideal theoretical curves, like the solid green line for the Büdöker-Landauer semi-classical time, we get a smeared out version, in this case, the dashed green line, which does not diverge as quickly because you're always really biased towards a slightly higher velocity. And the same thing is true for our weak measurement predictions for the in-plane and out-of-plane times. What do we actually see qualitatively? If we look at that in-plane time, we see it grows. It does not diverge, of course. It doesn't grow as quickly as the Büdöker-Landauer semi-classical time. And it seems to start dropping again at lower velocities. As you see, that's about a 1 sigma effect here. We have more recent data that I'm not showing that really nail that down, and we'll be submitting a paper shortly demonstrating that effect. And we see the out-of-plane time, the thing that shouldn't even exist classically, that up here in the classical regime goes to 0, but once you're in the tunneling regime, begins to grow. So we really confirmed that these weak value times are believable, and they behave in more or less the way that we expected them to. Now, as excited as we were to see that, I mean, we really had been working towards this on and off for 20 years. It just confirms a theory that I at least thought I knew quite some time ago. And it doesn't look that different, to be honest, from the group delay time that our group and others have already measured. What I think it really opens up is the possibility to ask deeper questions about the history. And here's the one we're working towards now. Don't ask how much time did the atom spend throughout the barrier. Ask how much time it spent just in this yellow region, or in this region, or this region, or this region, and find out, do transmitted and reflected particles have different histories? Here's the intuition. As thick as I make the barrier, eventually the reflected particle doesn't care. It was probably reflected in the first evanescent decay length. So you might expect that reflected particles never see anything other than the entrance of the barrier. While a transmitted particle, I know it came in from the left and I found it on the right. Shouldn't I conclude that it spent time everywhere along that path? Interestingly enough, if you do the calculation, that's not quite what you find. This red curve shows what we predict for the reflected particle, which is basically just psi squared. Almost all the particles are reflected, so there's almost no difference between asking about the reflected particles and asking about the whole wave packet. But if you ask, again, using this weak measurement formalism, but that's the correct way to predict the results of our experiments, what would happen if you look only at transmitted particles? You do get a symmetry. You have just as much information from the initial condition that it came in from the left as from the final condition that it exited on the right. But what you see is an exponential decay on the left and an exponential growth on the right, with essentially 0 time spent anywhere in the middle of the barrier. So once more, we raise this puzzle. How do particles manage to get across a barrier without spending too much time there? It seems as though the particles spend some time getting in and then spend some time getting out, but it doesn't care how much is in the middle. And we still find that very mysterious. And I'd like to have a deeper picture of that. But mostly, I'd like to verify this experimentally, really do the first measurement where we can demonstrate clearly that depending on the final state of your system, you have gotten more information about the history. You've learned whether or not it spent any time in this region over here. There's one caveat I'll mention, which is that here I'm only plotting the real part of the time, the in-plane precession, because I think that's really the right one to be asking about when you ask how much time did it spend. However, we've also calculated the imaginary part, and if you do that, you find it's essentially constant across the whole barrier. That just tells us something we know, which is that perturbing a barrier lowers the exponential transmission probability for the particle. And it doesn't matter where I add a little extra height to the barrier, it has the same effect. If you think about the WKB approximation to the transmission probability, that's very, very easy to see. But I would say that's telling me that the particle is equally sensitive to every region in the barrier. That's not the same as saying that a probe at any region in the barrier would be equally sensitive to the particle. Every time I even say that, I know it sounds confusing. And maybe that's the most basic lesson from tunneling times, which is that in order to answer a quantitative question, like how much time does a particle spend in a region, we need to turn it into an observable. And the way we do that is not by going to a textbook and asking what's the observable. It's by thinking about physics experiments and saying, what do I mean by a measurement of this quantity? And then writing down the Hamiltonian that describes that coupling to see what is the mathematical object that represents the measurement. Normally, however, we assume that a quantity that we can measure many different ways classically, like the position of an electron, really is a fundamental quantity. And it will have the same value no matter how I measure it. It turns out for time, which is not represented by an operator in quantum mechanics, and certainly not the time spent in a barrier, there are many different things you could imagine measuring classically that give the same result. And once you go to the quantum regime, there is no longer that guarantee. They're not necessarily giving you the same result. So what we've learned is just that there's a kind of coincidence. There are different observables that become equal in the classical regime, but they really have different physical meanings. So we need to learn, what are these different timescales? What are they describing? How would I measure each of them, and what are their values? Okay. So we're trying to set up to do that experiment. We're not quite there yet, but there's a really interesting spin-off that I also hope we can do in the lab, which began long ago when this was just, a pipe dream, but I was describing the proposal at a conference. And Bill Phillips said, why do you keep talking about this limit as b goes to 0 or making weak measurements? Why not just strongly measure whether the particle is in the barrier or not? And I very glibly said, well, if you strongly measure whether the particle is in the barrier or not, whenever you find it in the barrier, you, so to speak, collapse it to a wave packet inside the barrier, which automatically has enough energy to exist under that potential, or above that potential, I should say. And therefore, once you find it there, you've created real momentum components that can roll across the rest of the barrier without even needing to tunnel. So the prediction was that if you could strongly measure that a particle was in the barrier, even if the barrier was so thick that you'd been seeing no tunneling before then, you might still find it in the first exponential decay length. Whenever you did that, it would become essentially equally likely to be transmitted or reflected. So you could enhance tunneling by the mere fact of looking for particles inside the barrier if you look for them strongly enough. Now, we didn't really know how to look for them strongly enough. We imagined taking this probe, putting it at the beginning of the barrier inside the first exponential region, and making it so big that it did something like a pi pulse. Except I don't really know what that means. I don't know how to do that because we didn't know how long the particle is spending there. How do you tune something to be a pi pulse if the time itself is an unknown to begin with? So here was our more recent idea. Just last year, we started thinking about this. What if we stick with the small magnetic field, what I was calling a weak measurement before? We lower the strength of that probe, so there's only a very small rotation angle. But now I post-select. I post-select on the spin of this electron or atom. I only look at cases where it comes out along the minus x direction. So remember, it began in plus x. It only saw this field if it was in the barrier. There's no way I could ever find it orthogonal to its initial spin state unless it interacted with that field, and therefore unless it was inside the barrier. So there was our conjecture. Have a weak magnetic field confined to the barrier, and then look only at the minus x spin component, and that should be equivalent to having determined with certainty that the particle was inside the barrier. Will that then enhance the transmission probability? By which I mean, is the transmission amplitude for the minus x going to prove to be equal to the reflection amplitude for the minus x? So my student David Spearings simulated this stuff, and he found that my conjecture was incorrect. This doesn't happen, and the simple way to understand that in retrospect is that this time-independent probe can't change the particle energy. So there's no way that this could give the particle enough energy to traverse the barrier. And in terms of this collapse picture, what it means is that measuring that the particle was in the barrier at some unspecified point in time doesn't collapse it. That's not even a projection operator. It doesn't have eigenvalues of 1 and 0. It's a time integral of a projection operator. So here's what he found. Do the simulations. You look at this ratio of the transmission and reflection probabilities for the particle that ended up with the minus x spin. And on a log plot, you see that it's always exponential. It's exponentially more likely to show up on the right if the position where I put the probe, where I found the particle, is on the right. It's exponentially more likely to come out on the left if the position was on the left, which is really funny because what it means is it looks as though the particle shows up at this position where I found it, but it still needs to tunnel either to the right or to the left. And it has an exponentially decaying probability in either direction. It turns out mathematically it's easy enough to show why that occurs, but it's kind of provocative. More interesting to us, though, was to say, what if I do give the particle energy? So what if I try to collapse the particle at a particular time? How do I do that? Well, I pulse this magnetic field on for a short time, and it turns out you can show this easily in the delta function limit, that it then does what I was hoping. So here again is this plot, the ratio of transmission to reflected probability. This blue curve that just looks like an exponential function of position is what I showed you before. But the green curve shows what happens if the probe is very short. And what you see is that across most of the barrier, it shows equal probabilities for transmission and for reflection. In other words, it says that if you rotated the particle to that minus x spin, it doesn't matter, it almost doesn't matter where in the barrier you did it. You've now given it enough energy that it's equally likely to roll across to the right or to the left. So it really will act like collapse. And we think there's a path forward to actually doing this experiment, and in particular addressing the thing I don't immediately know how to answer, which is how short in time does that probe need to be to effect this sort of collapse. We know that the delta function probe does exactly what I'm describing. We know that the infinitely long in time probe just gives you that exponential behavior and never collapses it. We don't yet really understand where the transition occurs. I mean, we have the results numerically, but we'd like to have a good understanding theoretically of how short does an interaction need to be to collapse a particle into a barrier. I think that's a kind of deep question, so we're excited about pursuing that. I've been talking a long time, and although there is something else I wanted to tell you, I worry that your attention spans might not be up to it. So I wonder, with Paolo's approval, maybe I should invite questions on the first two parts of the talk, and then if people have the energy and time, I can say a few words about the third then.
Seems like a good idea.
So in that case, let me just skip to some conclusions slide, even though 1/3 of it won't mean anything to you, and open the floor to questions for now.
So maybe we can already thank Aephraim for 2/3 of his talk. And open up for questions and or comments.
Marcelo.
Hi.
Hi,
Aephraim,
Marcelo.
how are you
Great
doing?
to see you.
Nice to see you. I have a question. How you put that barrier? Is basically you change especially the modulation of your laser.
So the barrier is a blue laser beam focused down to 1 micron, which is as tight as we can do in the current geometry. As far as modulation, it's true that we use an AOM to sweep it in the transverse direction just to make sure that it's broad enough and flat topped enough to cover the entire waveguide. But other than that, no, there's no modulation just to create the barrier. There is modulation to create the Raman sideband. Okay. So we modulate at 6.8 gigahertz. It turns out that there's an interesting effect. The two sidebands you write with phase modulation have the wrong phase relationship. So one pair of sidebands gives you a Raman transition with one amplitude and the other 180 degrees out of phase with it. So we also have to go through a cavity and suppress one of the sidebands so that we end up with just the two. And that's what gives us the Raman transition.
And to control the position of that, that position of the mapping of the probe inside the barrier.
No, I see. So far we don't do that. And the easiest way to do it, of course, would be to have a completely separate pair of Raman beams and slide them around. At the moment, since the Raman beams and the barrier are the same thing, we don't have that control. We can only look at the integrated time over the whole barrier. So the two paths forward are either have just a separate Raman beam. Again, as I said, we can't focus anything in the current geometry smaller than 1 micron, so I can't put it inside the barrier. We could imagine a differential measurement where the barrier is here. Oops, where's the camera? There it is. And the probe is here, and we slide it across. And by looking at differences, we could still infer something about what the individual times are. The other possibility is to make the barrier wider and keep the probe 1 micron. And for that, I think we just need to do a little more cooling, because at the moment, if we made the barrier wider, the transmission would be too low for us to get any results. The other thing that we're looking into, which is a little more clever, which means we don't know if it'll work, is to use some additional field to tune in and out of Raman resonance. So in fact, you can even use the differential AC Stark shift due to the barrier itself to make the Raman resonance narrower than the barrier. And this adds a lot of complications, but it's what we're looking into at the moment.
Okay. Thank you.
Gabriel has a question, and then somebody next to me also has a question.
Hi, I actually have two quick questions. So the first one is, what would happen, you think, if the BEC was prepared in some kind of more exotic state, like a spin squeeze state or something like that? Would that change anything for computing the tunneling times and so on?
Great question. So because of two things you said, I'm not sure which way to interpret it. So I'll interpret it as two questions. One is, if the BEC were not just a simple Gaussian or Thomas Fermi wave packet, but something more interesting, well, then it would be the same as the equivalent Schrodinger problem. You know, we could ask, what's the tunneling time for this other wave packet? In fact, what typically happens is that in the monochromatic limit, you approach the tunneling times that you would have just calculated for a given incident energy. So the shape of the wave packet shouldn't matter too much until I'm so broadband that it's a much more complicated problem. There are, of course, also effects due to interactions between the atoms, and I didn't talk about them. We tried to do this experiment in a regime where those were pretty negligible. We confirmed that. But of course, for the future, it's very interesting to turn on the full Gross-Pedayevsky dynamics and see what happens to the tunneling time when every atom is tunneling in an environment created by all the other atoms. And I don't even know the answer to that problem yet. So I think that that's quite good. But you mentioned a squeezed state. And to me, that's actually the way that you learn why I shouldn't treat the in-plane and out-of-plane angles on the same theoretical footing. It turns out that for a spin 1/2, you just always have these in-plane and out-of-plane angles. And you might realize for a spin 1/2, there is no squeezing. You can't squeeze a spin 1/2. If the spin we were using were larger, then indeed I could squeeze the state, and that corresponds to making the measurement have better or worse resolution, because I'm trying to make this blob precess on the Poincare sphere, the Bloch sphere. And if it's phase squeezed, then I can detect that rotation more accurately. If it's number squeezed, or Z squeezed, then it becomes harder. So the Z squeezing makes this a weaker measurement, and the phase squeezing would make it a stronger measurement. And in calculations, what I showed is that the precession angle remains the same in all of those cases. It doesn't care how squeezed you are, but the alignment angle disappears as you make the measurement weaker. So that's kind of my justification for saying that the precession angle really is this independent feature of the system, not dependent on details of the probe, while the alignment really tells me about back action to the probe and is therefore sensitive to whether or not the probe was in a squeezed state.
Okay. And so my other question would be, just so I can understand a little bit better the physics, what would kind of change if you were able to measure the photons scared from the trap? So the standing wave that's generating the blue trap in the drawings, if one could measure the scattered photons, would that mean serve as a detector that the particle is in there somehow?
Mm-hmm. Yeah, I think if you imagine a regime where you could resolve the momentum change of an individual photon while the particle is in the barrier, that would be an example of this strong measurement I was talking about before. And when we were originally talking about those things 20 years ago, that's exactly what we had in mind, is have some kind of a fluorescence probe and what happens when you detect the scattered photon. And how do you do that without just giving the atom energy in a rather trivial way, just the transferred kinetic energy from that recoil or something like that. Of course, the kinds of interactions we're using, these dipole forces due to far detuned laser beams, there's essentially no spontaneous scattering. There's only a kind of Bragg scattering-like thing where you absorb one photon and you're stimulated to emit a different photon with a slightly different momentum. But that occurs when you're exerting a force on the particle. So in fact, it doesn't occur so much in the barrier as on the edges of the barrier, right? The regions where there's a big force. So it probes something slightly different from what you were asking, but I think it's also a very interesting idea.
Okay, thank you very much.
Thanks for the questions.
Okay, first, let me congratulate you on a very beautiful experiment and a very clear colloquium. I have two questions. first, since your proposal is based on the transport of a clock through the barrier. Now, according to Einstein's general relativity, the rate of the clock is affected by a gravitational field. Of course, you don't need Einstein for the Earth gravitational field, which is very weak, but you can assume that you're doing the measurement in a strong gravitational field. And the question is, how would that affect your measurement?
Wow, you're always to be counted on for asking more interesting and complicated questions than I'd anticipated. I'm so grateful to have you in the audience at this talk. I've certainly never thought about general relativistic considerations for this experiment. It seems to me that it's like any other clock, the same thing that would happen if I didn't have a tunnel barrier and I were measuring the classical time. The clock is, of course, going to tick at a rate determined by the local metric. I guess the problem only becomes difficult if you imagine that the gravitational field has a gradient, right? That the clock rate is position dependent as I tunnel. But even in that case, it seems to me that instead of just asking about, unfortunately, I didn't set this up to annotate. Instead of just asking about the integral of the projector onto position X, integral dx of that, I would have a new weighting function that at each position X, I might have a clock that ticks at a different rate. So I would need to look at this integral of, g of X projector onto X. And in fact, experimentally, that's what's really happening, because we don't have a square barrier, we have a Gaussian barrier, and we don't have a square probe, we have a Gaussian probe. So the thing we've really measured is a Gaussian weighted integral of the projector onto all positions.
Okay, the second question is, I learned quantum mechanics. My first teacher was David Bohm. And since you have discussed the connections with measurement and quantum classical boundary, what would you think about, well, there's recently been a kind of revival of Bohm's interpretation.
Yeah, that's something that a number of groups, again, back in the 80s or 90s, were trying to apply to tunneling. And in fact, I thought about it a lot in those days. Remember that I mentioned early on, well, I don't have to tell you, but I'll repeat it for the sake of the rest of the audience, that one way of thinking about the superluminal propagation is to imagine that the particles in the front of the wave packet got transmitted and those in the back didn't. When I first thought of that, which made sense for a classical packet of energy, but I tried to imagine it for a single particle, I was very troubled because we don't normally think that a particle has a property that tells you where in a wave packet it is. How can a particle know where it is relative to the rest of its wave packet? Except in Bohmian mechanics, where of course there's a wave and also a particle. And there are particles in the front and there are particles in the back. And for very simple reasons, in Bohmian mechanics, different particle trajectories are forbidden from crossing one another. So in one dimension, it's very clear then that if some particles are being transmitted and some are being reflected, it needs to be the very first incident particles which are transmitted and the later ones are all reflected. So Bohmian mechanics is great for reinforcing that intuition that kind of saves energy causality, if you like. However, the delay times themselves behave very strangely, and I kind of became disenchanted with the time from that perspective. But you may realize a few years ago, we did an experiment tracking Bohm-like trajectories for photons in an interferometer. And Bohm's longtime collaborator, Basil Hiley, asked why we don't do the same thing for the atoms. And in fact, in principle, that's possible. We could imagine doing weak measurements that would allow you to reconstruct the Bohm trajectories for atoms as they tunnel through the barrier. It would be a very difficult experiment. I'm tempted to do it, and I'm also tempted to let someone else do it. We'll have to see, but it is conceivable.
Thank you very much.
Oh, thank you.
If there are other questions or comments. Otherwise, Ephraim, would you feel encouraged to go on and tell us about the third
I think what I would feel encouraged to do is to advertise the result. I'll pose the question and put up a picture of the result and skip everything in the middle to convince you that you want to ask me more about it, you want to look for the paper, and if you're the referee, you want to be kind. Would that be all right?
Yeah, sure.
So let me jump back down a few slides. In fact, let me jump to here. Here's the easiest question. I'm going to begin in medias res here. We're interested in looking at nonlinear effects. And we did an experiment a few years ago where we measured the nonlinear effect a single photon could have on a second beam, a probe beam. And we did that using a kind of dispersive nonlinearity. But now we asked ourselves about another kind of effect. One way you can get an optical nonlinearity or a cross-phase modulation is shown here. Let me jump, oops, no. Shown here. I have a probe off resonance, and it's seeing an index of refraction shown here in red. If I now add some beam on resonance, let's say for a different transition, the first thing that happens is I excite some of the atoms to the excited state, and that bleaches the sample. It lowers the index of refraction because the excited state and ground state atoms have opposite indices of refraction. So we can see a phase shift on the probe that changes based on the intensity of the signal. And even a single photon signal pulse might change the phase of the probe. The way I like to think about this now is to say that since the probe is only studying the ground state atoms, it's sensitive to how much time atoms spend out of the ground state. So we can use this nonlinear effect, this cross-phase modulation, to just measure how long are atoms spending in the excited state. And the question I want to ask is the following. As light propagates through a cloud of atoms, how much time does it cause the atoms to spend in the excited state? We all have this picture that the photon excites the atom, and then it takes a while before the atom realizes, oh, energy conservation was violated, I'd better drop that photon, spits the photon back out, and that's even a hand-waving way people explain why light travels slower through atoms than through air. But what if I look only at the photons that are transmitted? Normally, the way I think about transmission and absorption in a sample is that some photons get absorbed by atoms. Once they get absorbed by atoms, they're going to have to spontaneously emit. And on resonance, that's the only kind of absorption you have. So the transmitted photons are the ones that just never got absorbed by any atoms. So this led us to the thought that if I have this signal beam on resonance, and I try to measure how long do atoms spend in the excited state, maybe I'll find that whenever a photon is lost, right, spontaneously emitted out to the side, I'll find that there was an atom that spent on average a lifetime in the excited state, and that affects my probe beam. While whenever I see a transmitted photon, I'm now looking at a case where no atom was ever excited. I just got lucky and the photon sailed right through. So this would mean that there would be zero nonlinear phase shift for a transmitted photon, and that all of the nonlinear phase shift in this saturation kind of nonlinearity comes only from absorbed photons. And in fact, this is what we were expecting to see. Here's how we do the measurement. We send in some pumped photons. We send through a probe beam and we measure the phase shift in the probe, which I'm arguing is a measure of the amount of time spent by atoms in the excited state. So the time integral of the expectation value of PE. But then we allow our incident photon beam to hit a photon detector that either sees a photon or doesn't. And we ask, what's the phase shift only when it does see a photon? We did this experiment not with the BEC, but just with a magneto-optic trap, rubidium 85. And as I say, we built on some earlier experiments. I don't want to go into the details, the tricks that went in here, but here's some of the remarkable data that Josiah, Daniela, and Kyle were able to accumulate. These upper plots are the classical cross phase shift we see if we send in pulses that have about 34 photons in them, and you see the shaded region there about 20 nanoseconds across. We get a negative shift for negative detuning, positive shift for positive detuning. But if we now look at the effect of just a single photon, it becomes quite hard to extract from all of the background noise. And that's why in these lower plots, you see some very slow variation, but we fit all of these curves to a slow variation plus a peak of this shape with unknown amplitude. And what you see here are the best fits. And you see that on the left, these two different examples, seeing that extra photon seems to give us some extra pulse. On the right also, some extra pulse, but with the opposite sign. And if we put it all together, we find on the right, as a function of the average single photon phase shift, that it looks as though our transmitted photons have about the effect of 4/5 of an incident photon, which is interesting because our simplest picture suggested that the photons that were transmitted because they didn't get absorbed by any atoms and therefore should not have affected the probe beam. And we pretty conclusively ruled that idea out. So we have to do a little more work, a lot of experimental work, but also some theoretical work to understand how to think about it. At the moment, we think this is mostly because our pulse was so short that there are actually very complicated dynamics on the block sphere, even for a single photon. And that's something that we weren't understanding properly for a while. So we want to redo the experiment with either a lower optical depth or a lower bandwidth. And what we expect is that we will find for narrowband pulses that this time goes back to 0. And we have a kind of theory, a sort of semi-classical theory that becomes roughly consistent with the experiment, but we don't believe it's the full story. And as I say, I think we're just opening up more questions about the past behavior of quantum systems. You might not have ever asked yourself before, but it's one thing to ask, how much time do atoms spend in the excited state when I send a resonant laser beam through the atoms? Well, we know how to calculate the average polarization and so forth. It's very different to ask, if I send one photon into that cloud of atoms, what can I say about how much time they spent in the excited state, depending on whether I find the photon transmitted in the end or scattered to the side in the end? And I think this is the first time anyone's really tried to measure that. And I don't even think we have the full theoretical answer yet to that question. So hopefully there are many more examples of this where now that we have experimental capabilities for controlling and probing individual quantum systems, we can really start looking at what we learn from that post-selection, what we learn from seeing the particle hit one point on the screen as opposed to another. And once more, that's back to these conclusion slides. Summarizing, we did find a non-zero tunneling time for the photons, despite the work that was published last year. It's about 0.6 milliseconds because everything is so slow in these laser cooling experiments. And we do expect that in the future, we'll be able to learn how to collapse the atoms into the barrier region and see that that gives them enough energy to leak fully across the barrier. And we've also begun to measure how long resonant photons spend as excitations in the atoms. And we're going to keep doing those experiments as well. So thank you for your attention to the third of my talk. And if there are further questions, I'm very happy to try to address them.
Anybody like to ask another question? Just regarding this last part, Ephraim, I would think that this time the photon would spend, or the atoms would spend excited, probably depends a lot on geometry, on collective interaction of atoms with light, right? Whether you have a kind of a Dickey cooperative effect or not. And I'm not sure I follow when you say zero delay, whether you're taking stimulated emission into account, meaning that the photon could go over many Rabi pulses.
Okay, so yeah, I think you're touching on a lot of the important issues. In terms of the geometry, you're right. The assumption I was making, we're talking about a pretty macroscopic sample where there are many, many modes you can spontaneously decay into. And for that reason, my working hypothesis had been that once you excite an atom, it's much more likely to decay into those other modes. We can neglect the forward emission, almost neglect it. Stimulated emission is an interesting worry, but remember, I'm asking about the single photon case, so there is no stimulated emission. There is, however, a kind of coherent emission that you see just in the Bloch sphere dynamics. And this is what we think is the right story for the short pulses, that when you have a short enough pulse, as it propagates, it actually evolves into a kind of 0 pi soliton, where the envelope goes positive and then goes negative. And what that means for the Bloch sphere dynamics is that you start by coherently driving the atom, coherently driving the atom up from the ground state, and then you coherently drive it back down. So you don't leave any excitation in the atom, and there's no time for any spontaneous emission. And certainly a short pulse like ours, that's what you'd expect to happen at the semi-classical level. What wasn't immediately clear to us is that that was also a fair description at the single photon level, but I think it actually is. The problem is this is a semi-classical treatment. There's no way to discuss the entanglement between the final state of the photon and the atoms. So although we can use it as a motivation for saying, oh, there actually is a lot of coherent forward scattering, and that's why even photons that go in the forward direction may have first caused the atom to spend time in the excited state, I can't separate the two pieces unambiguously. For that, I think we need a fully quantum treatment, and we're working with a few people on different versions of that right now. Excellent question, though. You really touched on all the important points.
Interesting. Any other questions or comments? I don't see anybody raising their hands. So then let's thank Aephraim again for a very, very interesting, thought-provoking, and motivating us to continue following his work.
Yes, please do that. Well, thank you all for inviting me and for being here. And I've enjoyed the opportunity to talk to you and get such provocative questions.
I think we can probably, I'm not sure the YouTube has been, live feed has been shut down. We can probably do that. Adrian, you want to say something?
No, just say thank you in the name of the research committee. Just say thank you for accept the invitation.
And thank you again.
Thank you.
Okay.